Good afternoon. I'm DK Panda from Ohio State University. I'll be presenting here the Unified Runtime for PGAS and MPI over OFED. This is a joint work between me and Santhan, who is sitting there. So I know this session is always hard, like immediately after the very nice meal. So it'll be good if you people ask questions. That will keep you awake and me awake also. Okay. So what I want to do here, like there's a lot of discussion going on in the all earlier Open Fabrics workshops. We have talked a lot about MPI, and MPI is getting matured. A lot of deployments are taking place. And now we are always looking forward to the exascale computing. And in that context, this discussion comes saying what will be the programming model for these next generation systems. And in that context, I'll try to introduce the problem, then give some challenges in unifying one of the PGAS model, which is the UPC, which is commonly used, and MPI, try to provide some design solutions and experimental results, and then I'll conclude the talk. So the PGAS stands for Partition Global Address Space, and this is especially gaining interest because as we are trying to scale these large-scale systems, like if you're thinking of like exascale systems, Steve indicated in the morning, we'll have like millions of cores, a lot of concurrency. So the question is, can MPI handle it? Okay. Obviously, that is always, it's like the good old problem of Fortran. You know, when Fortran will be dying, the same thing will happen. I mean, MPI will continue to remain, but at the same time, other kinds of programming models will come up. And especially people are focusing on the PGAS with a global view so that it improves programmer productivity. That means it is a global address space, so that means any process can access, any process or thread can actually access any memory in the system, which currently MPI cannot do. And then you can provide like language and compiler support to improve the performance. And one of the thing is the Unified Parallel C or UPC that has got traction over the last several years. Is one of the popular PGAS languages, and people want to use it over OFED. But there are a lot of problems. So let's see what are the problems, and then we'll try to see how to solve these problems. Now, currently, like all these parts of the big applications and the third-party libraries, whatever is running on all these pedestal systems, use MPI. Okay, so it is not like over the night people will switch to PGAS. So same thing happens a lot of like parallel math, physics libraries, etc. They have very high investment. This has been done over like last 20, 30 years. Again, you cannot just immediately go and rewrite them. Okay, so in that context, like we'll see a gradual growth so that people will try to move from MPI to any of the other PGAS like UPC, and we may need to have some kind of an hybrid. Okay, but then the question is, can we have an environment where both can exist, MPI and UPC? Currently, they don't interoperate very well. I'll show some slides. And even though like there are UPC, there are some available solutions, like the popular one is the GasNet from Berkeley. I'll show some numbers and their designs, and you will see that it doesn't deliver very good performance over OFED. It also doesn't scale. Okay, so then many times you might have seen a lot of presentations from different groups, like they will show, okay, this is how MPI performs, this is how UPC performs. Okay, but if you go and ask some details, it is like two different stacks. Okay, so it's like comparing apple to orange, not apples to apples. Okay, so you cannot make a lot of sense out of those numbers because MPI has been taken in one stack with one platform, and the UPC has been taken with another platform, another stack. So they are not using the same common runtime system. So those numbers are very misleading. In fact, a lot of people still present those numbers, but they're not strictly correct. And then a lot of focus is going on. People are talking about exascale systems. We'll try to do hybrid. That means UPC within the node, because a lot of cores are coming, and then MPI across the node. But where is the software stack to do that? In order to have that, you need to have a stack where you can have both MPI and UPC working together. Okay, so these are the kind of problems. So why can't, let's say, UPC work with MPI? So here it is a small illustration. So here it is trying to show like a UPC. This is a mem gate operation, and then there is an MPI barrier. So we are trying to combine here. So it has two different runtime, UPC runtime and MPI runtime. And here the other process, P1, is trying to do some local computation and waiting for the MPI barrier. So let's say this P0 sends a mem gate request. What is going to happen is this P0, since it has initiated a UPC request, the UPC runtime will actually be waiting for the results to come. On the other hand, P1 has actually is doing a local computation and then going to MPI barrier, and it is waiting in the MPI runtime. Okay, so both are they are not synchronous. So one is within the UPC runtime, and the another one is the MPI runtime. So in fact, this will lead to deadlock. This is a very, very common issue when you are trying to combine both these things together, because message in one runtime, but the application is waiting on the another runtime. So the current prescription, the way has been done is to put some barrier on one mode. So even though you have both UPC and MPI, you try to put artificial barriers so that at any time, all the processes are either in the MPI or in the UPC. Okay? And obviously, you can see that it's like a putting force barrier, and this leads to very bad performance, and we cannot tolerate that. Okay? So now let's say with this kind of background, let's see what are the additional challenges if we want to unify the UPC and MPI. So here, they show some stacks through which, various ways, people use the UPC and MPI. So of course, this is a pure MPI stack, like MPI application, and here we have an MPI like our MVAPICH 2 from OSU, then it has MVAPICH 2 optimal runtime. This is, let's say, running over InfiniBand network with OFED verbs. So there are a lot of people are using this. So then if you have the UPC, like the GasNet from Berkeley, this is how it looks like. You have UPC application, goes through UPC compiler, then you have a GasNet interface and UPC runtime, and then it goes through the GasNet IB verbs. So GasNet actually has IB verbs implementation and the runtime, and it runs over the InfiniBand network. But we'll see that this exact stack is not as scalable when you compare an equivalent MPI like MVAPICH or MVAPICH 2 implementation. Okay? Now the UPC stack also provides another way to run, and this is if you combine a UPC, pure UPC or UPC plus MPI application, it can go through the MPC compiler runtime, but it can run on top of MPI runtime. Okay, so in fact, GasNet from Berkeley provides this flexibility, but then it can actually run over MPI, then the MVAPICH 2, and then MVAPICH 2 runtime, and then IB network. But here you will see that UPC semantics don't get mapped very well to MPI. I'll try to expand on that in the next few slides, and that leads to bad performance. So you can interoperate, it will run, but you will not get the good performance. Okay. So then the question is, can we place UPC on top of MPI? So the UPC is mostly based on active message, okay? And in short, we'll call AM. And they are not part of the MPI, and this is very critical to UPC. The entire UPC stack is based on active messages. And UPC is typically a lighter weight, so putting on top of MPI, you lose the performance. And then there are other various kinds of mismatch. So in fact, there has been a lot of discussion going on in the MPI 3 forum to resolve some of those things, but it may not be resolved all completely. So then the challenge now lies in the path forward. That means can we unify the runtimes, but not the programming models? Instead of saying the programming models get unified, we'll see whether over the same OFED, we can unify both the runtimes. Okay? So that leads to our problem statement. So we started working on this almost 6 to 9 months back. Our objective is that can we design a communication library for UPC, which is scalable, first of all, on the large InfiniBand clusters, and it can provide equal or better performance than the existing runtime. Then the second goal was that can this library also support both MPI and UPC? So when they run individually, it will try to deliver the best performance. Okay? So even though we are trying to unify, we will not slow down anybody. The MPI will run in the best possible manner, UPC will run best possible manner, and if they can be run at the same time, that will also try to deliver the great performance. And also we'll see there are issues about the memory consumption of the library, and we want to also keep that reduced. And then if we can develop this kind of a runtime, this will satisfy the bigger objective, which is it will allow the scientists to develop applications in any of these following modes. You can write MPI programs using the same stack. You can have PGAS, or in this case UPC, or you can also try to write hybrid programs. And that way, it will really allow the scientists to evaluate the impact of the programming models on applications on the next generation systems in a fair manner. You take the same application, now you can run in either of these ways and then see what is the best. And we'll show some examples. We'll see that if you can do the hybrid, in fact, you get the best performance. Okay? Any questions so far? Everybody's awake? Okay, that is a confirmation, okay. So let's see how we tried to resolve this. So here it pictorially it shows how we wanted to resolve this. So think of like any programming model. I mean, even MPI or UPC or you say Chapel or global array, you name anything. If it has to run on OFED verbs, it has to work on the exactly similar manner. Like you have to handle the connection management, you have to handle the buffers, you have to have some queue pairs, because these are the common things which work with the OFED, and you have to utilize all those things to design your runtime. So in this case, what happens is the MPI, like we have the MVAPICH to runtime, buffers, queue pairs. Similarly, like UPC stack has UPC compiler, GASnet, then they have also have a similar things. But then the question is, do we need to duplicate all these things? Okay. And not only like a duplication, if some features are exploited here, you also need to exploit the similar features here. On the other hand, can we actually combine these into this green one? So that is exactly the same runtime, okay? In fact, the additional, the inside the resources, it'll use, whether it is an MPI message or the UPC message, they will exactly use the same connection, same buffers. In that case, we don't have to reinvent the effort, and whatever enhancements we do, or tomorrow there's some new OFED verbs get introduced or new mechanisms get introduced, both will get benefit. Okay? So that is the overall the idea. And we have done this, our work called UCR, which stands for Unified Communication Runtime. So in this case, the way we have done is like, just like MPI, some of you are familiar, like it has eager protocol, rendezvous protocol. Similarly, there are active messages. Then you can do a lot of optimizations, like you have some send short active messages without arguments, or you can have some short active message again without no data payload. If you have some medium active message, then you can use, some of you are familiar, MVAPICH to use something called a RDMA first path. You can try to utilize that logic as the bounce buffer. If you have a large active message, then you can go through RDMA put. You can also go through on-demand connections. So what we are trying to do is, whatever we have done in the MPI, we are trying to take similar kinds of mechanisms to trying to support the UPC kind of messages. So then also GASnet has extended interface for efficient remote memory access or RMA. There again, you can try to exploit some of this inline put, or if it is a medium size put, it might be internally buffered. If there is a bulk put, then we can have send buffer will not be touched, no buffering. If there is a get operation, we can do RDMA read. So we are taking all the UPC kind of the semantics or the mechanisms, and then trying to match with what we have done in the MPI, and then trying to unify those things. So here it shows some pictorially how we have done this design. So think of like, let's start with first the MPI library design. So here we have a MPI library sender, HCA is connected through the network, and then MPI library. So let's say MPI messages. Then, as you know, we have some set of connections. You have to establish the connections, and then you send the message here, and then it goes to a message queue. Okay, so this is how all the MPI designs currently work. So now what we can do is we want to utilize exactly the same resources, and we want to share them. So that means if it is a UPC message, we don't have to establish separate connections. It uses the same connections, and it goes through the same set of resources, and then on the other hand, it goes to an active message handler. Okay, so in that way, we are trying to reutilize all the things what we have done, and then RDMA for large active messages and put and get kind of things. So we had seen these three stacks earlier, and we saw there are the limitations. So what we have done here is that we have now unified these two parts, like the GASnet MPI runtime, and then the MVAPICH to MPI standard interface. So we have combined this, so that is our unified runtime. So we exactly use the same data structures, same resources to take MPI messages or UPC messages across the nodes. Now that is not the only the challenge. Now what is happening is a lot of multi-core nodes are coming. Okay, so these days in the single node you have like 48 cores, 96 cores kind of things. So in fact, UPC allows the thread model. Okay, the MPI is always like a process-based model. So here you can run multiple threads. So this is a little bit of dense slides, but what it tries to show that there is if you have the same HCA, but you have a lot of cores, so then the different ways you can run. In this example, here it says like there are multiple UPC threads, but there is only one communication thread. Okay, so here we call like a multi-threaded, multi-endpoint runtime with a communication thread. On the other hand, here it can be, we don't need any separate communication thread. It can be all UPC threads. And in this case, we can try to even do better, like a work stealing for load balancing. That means whatever amount of work needs to be done within a node, any UPC thread can pick it up and perform the operation and send the messages. So in our latest design, we have actually both these models supported. So now let's see some of the results. I mean, these are like some high-level designs. We published a paper in October last year. It is available on the web. I'll send some pointers so you can take a look at the details, but see how the results come out. So this has been done in the context of, on the top of MVAPICH 2. As you know, like we have MVAPICH and MVAPICH 2. MVAPICH is getting old. More people are using MVAPICH 2, so we have done this design with the MVAPICH 2. So this is like the very quick update on the MVAPICH 2. We made a release 1.6 a few weeks back. The total number of organizations continuously, steadily increasing. Currently, the number is more than 1,500 organizations in 60 countries. We see a lot of downloads from OISU directly. Almost these days, like every week, we come very close to 1,000, 2,000 downloads per week, kind of thing. So this is what is happening. A lot of downloads are taking place. So we are trying to do it in the MVAPICH 2 context here. So we try to compare our design with the Berkeley's GasNet, their latest version, and also they have a shared memory optimization. So we try to give all the best benefits to the GasNet design. Then we have different kinds of environments with different platforms, Intel Nehalem, ConnectX QDR, with Intel Clovertown, DDR, and some AMD Barcelona with ConnectX DDR, and I'll show some of those numbers. So let's start with some very basic micro benchmarks. So the micro benchmarks here, just like in the MPI, you know, like there is a latency, bandwidth, bidirectional bandwidth, multi-pair, similar kind of things. In the UPC, there are a lot of micro benchmarks. So here it says UPC memput. So that means you are trying to write some sort of data using the memput operation. So there are three designs here. So the coloring scheme is this. The blue one is our new design. And this is the GasNet IVV. That means this is the Berkeley's design, GasNet design, which is natively over InfiniBand. And then this is the green one, is the GasNet design, which is passing through the MPI, like passing over MPI. So GasNet with MPI, then going through InfiniBand. So obviously, whichever goes like over the GasNet MPI, so the green line, you will see it's not good performance because there is a mismatch. So even though it interoperates, you don't get good performance. But the red and blue, so the blue is actually behind the line. So they exactly match with each other. So what we are saying here is that exactly whether you do the GasNet basic InfiniBand design versus our basic design, they are good. This is only point-to-point. Later on, we'll see some applications and scalability. There you will see some differences. So this is also like a mem-get. Again, the similar trend we see. The GasNet UCR performs identical with GasNet IVV. That is the blue and red line here. And then due to the mismatch of the active message semantics with MPI, leads to worse performance for the GasNet MPI. So that is only point-to-point. Now let's see, we are trying to scale. Okay, and this is here the difference comes out. Let's say you are trying to run here. We are just trying to run a UPC Hello World program, just like the MPI Hello World program. It is running with 16 processes to 256 processes. And here we are trying to see how much memory is being consumed. And this is a big significant thing as you are trying to scale. Your library should not be taking a lot of memory. So here we are trying to see that. So this is the red one, which is the GasNet IVV. You can see that it is steadily increasing, whereas the blue one is more or less remaining constant. And this is actually the paper, which is available on our website. You can take a look at that. So now I discussed also the multi-endpoint. So here we have explored all different kinds of design, like either a IVV process-based or thread-based. Then on the UCR, we have a global log versus fine-grained log versus a multi-endpoint. And the best numbers we see here is the multi-endpoint. So here you can see that we are able to take like multiple UPC threads, go through the same adapter, and then send the data, and we almost get like a 80% improvement here. And the bandwidth also, like if you see around a 1K, which is a very short message range, we are significantly improving from 72 to 202 megabytes per second. And these are some numbers here where we have actually run the UPC NAS benchmarks. So that means the same NAS benchmarks, they have been coded with UPC instead of the MPI. And here we are trying to see like a 64 process and 128 process for MG, FT, and CG. And here you can see that compared to the GasNet IVB, which is the red line, this is the time. So the blue lines are always like better. Here we see around like 10% or 23% improvement just for with 128 processes. But then we went one step further because our runtime now not only allows MPI, pure MPI program and pure UPC, we can also combine it. So we took the NAS-FT application and we tried to redesign it with a hybrid MPI+UPC. That means UPC within the node and MPI across the node. And here you see there is a significant benefit compared to in the blue line. Now the purple line, we get almost 34% improvement. And that's exactly what people have been thinking of. Like when we go to these exascale systems, we can try to write our programs using these hybrid programming models to get the benefits of this multi-core trend, the shared memory within the node, and the MPI across the nodes. So to summarize here, what I demonstrated that we can actually try to design a unified communication runtime which can support both MPI and UPC simultaneously using the OFED verbs, and this has a lot of promise. Here, what we are trying to show is the MPI communication is not harmed. Similarly, the UPC communication is not penalized, but we are trying to get the benefits for MPI, UPC, and the hybrid. Okay? And what I showed here is like some of these benefits numbers, what we see not only for point-to-point, also the multi-endpoint version, and this runtime will actually try to solve problems using multiple programming modes. So it will give a lot of flexibility for the scientists to write their applications using only MPI or PGAS only or hybrid, and it will be a good suitable candidate for the exascale computing. So with this, I'll stop here, and I'll be happy to take questions. Yes?
So when you implemented the combined communication libraries, you plugged in an MVAPICH to do that as a net mod? How do you do that?
No, this currently has been done with the CS3 interface. Okay, so this is not available on the Nemesis side.
On the Nemesis yet, but so I'm still trying to figure out how both of them share the same.
So it has been like the CS3. You can think of it has been revamped or redesigned. Okay. So it is not just taking it and then adding something. So we have totally redesigned the underlying data structures and all so that both can be supported.
Are you planning on moving any of that infrastructure to a net mod?
Yeah, so CS3, the most of the people use CS3. So that's why our current focus is CS3. Gradually, people are moving to the Nemesis side. So once a lot of users move there, we'll be happy to move our design to Nemesis side also. Any other questions? Okay, thank you.